Hello everyone. We are going to discuss Ampere Circuital Law here. This Ampere Circuital Law is very important. So as I discuss, go through the topic very carefully and see to it at the end of the video. If you find anything which is doubtful or anything which you are not able to understand, you must post the doubts. Ampere Circuital Law states that the line integral of magnetic field around any closed circuit or loop is equal to mu naught times the total current threading or passing through this closed circuit or loop. So you need to understand here, line integral of magnetic field here means integration B dot dl. dl represents the small length. If we integrate it with respect to the magnetic field B dot dl, integration B dot dl over a closed loop, then it will be equal to mu naught times the total current threading that closed loop. It means the total current which passes through that loop. To understand this even more better, we will use a figure here. See, in this figure we have taken a closed loop here in the form of a circle. As you can see here, this is the closed loop. Okay, and we have taken a straight current carrying conductor where the current is I. Now this is a closed circular loop through which current I is threading, that is, it is passing through it. Now, as the definition or the statement of Ampere Circuital Law says, that line integral of magnetic field, that is integration B dot dl, will be equal to mu naught times the total current threading the loop. So the mathematical form is integration B dot dl over a closed loop for which a circle is given on the integration sign is equal to mu naught times the total current threading the loop. Now you need to understand what is total current. Like here, through this circular loop as it is shown here, the total current which is passing through it is I. Now suppose, let me take an example here. Suppose I choose to bend the wire somewhere. Suppose this is the wire which is going, and I bend the wire and I take the wire in this path as it is shown here, and then I make it to pass through it again. I make it to pass through it. The current here is I. Now the formula for integration B dot dl will be equal to mu naught into I is the total current threading the loop. Now here the total current threading the loop is 2I, I plus I, so that is 2I. So here a 2 will come, which will show the total current threading the loop, 2I. So I hope this is clear to you. I here represents the total current. So if this is clear, you need to understand one more thing here, that is the closed loop, as in the form of a circle we have shown here. This closed loop where the Ampere Circuital Law is used is known as Amperian loop. Okay, so it is known as Amperian loop. If you remember, if you recall, in the first unit of electrostatics, you have studied the Gauss theorem, where the surface, the closed surface in which the Gauss theorem is used, is known as Gaussian surface. In the same way, the closed loop here is known as Amperian loop. I hope this is clear to you. Now we will see and that this relation, that is integration B dot dl is equal to mu naught into total current threading the loop, how it can be proved. So we are going to prove it for a straight current carrying conductor. Suppose this is a straight current carrying conductor we are considering, and we are going to prove it for this straight current carrying conductor. Now we take a loop here, circular loop of radius r, and the center is the point where the current conductor is threading that particular loop. That is, it is passing through that loop from that particular point. Now, we know the formula for magnetic field due to a straight current carrying conductor. It is given here. You can see here, I am highlighting it. It is mu naught by 4 pi 2I upon r. If you remember, it is mu naught by 4 pi 2I by r, where 2 and 4 cancels out and we have the value of mu naught by 2 pi I by r, which is shown here. I hope this is clear. Now, what we are going to do is we are going to find the value of magnetic field. We are going to prove that magnetic field, integration of magnetic field over a small length dl, integration B dot dl is equal to mu naught into the total current I threading the loop. So we have the value of magnetic field here, which is given by mu naught by 2 pi I by r. So according to this value, we move to the next slide. See here. What we are actually going to do is we are going to calculate that integration B dot dl, and it comes out to be mu naught into I. So integration B dot dl, where we have solved it, where B dot dl, you can see here from the figure that B and dl, the small length element dl and the magnetic field B, will be in the same direction, so the angle between them is 0. So B dot dl is represented by B dl cos 0, that is B dl. Now we have, according to the Ampere Circuital Law, the mathematical form, integration over the closed surface B dot dl can be written as integration B dl, because we have already shown here cos 0, which is 1. So B comes out integration dl. dl is the small length. If you integrate it, you will get the whole circumference here. So which is, if we write the value of B from the previous page which we have considered, there it was mu naught by 2 pi I by r. We have written the value of B into the total length, which is L here written, which is given by 2 pi r. So we are having the formula here, which you can see here. So 2 pi r and 2 pi r will cancel out, and we will be left out with the formula which is needed. So that is the proof that integration B dot dl over a closed loop is equal to mu naught into I. Okay, so I hope this is clear to you. Now you see here, that is integration B dot dl, we have written it here as mu naught into I, which has been proved. Now what we are going to see here is an application of Ampere Circuital Law. Whatever we have derived till now, it was the definition of Ampere Circuital Law, then we have proved the Ampere Circuital Law. Now let us see a simple application of this Ampere Circuital Law. Suppose you are given a straight current carrying conductor I, and at a distance r you are asked to find the value of magnetic field. Okay, so you want to find the value of magnetic field at a distance r. What you will do is, taking this point at the center, you will draw a circular path which will represent the Amperian loop, which is a closed loop, and you take a small length here in that loop, which is dl. The direction of dl and the direction of magnetic field will be same. So if the directions are same, so integration B dot dl will be given by integration B dl cos 0 degree, and which cos 0 is 1, so we write here B dl. B comes out of the integration sign, so it is integration dl only. Now dl is the small length. If you integrate it, you get the total length of, or the circumference of this circle here, which is 2 pi r. So we write here B into 2 pi r. This is the value of B dot dl that we have obtained. But according to Ampere Circuital Law, integration B dot dl is equal to mu naught into the total current. So what we have written here in the left hand side, we have written the value of B dot dl, which is mu naught into B into 2 pi r. This is the value of B dot dl, integration B dot dl. We have written the value here, and in the right hand side of the Ampere Circuital Law, we are writing mu naught into total current threading the law. So if we see from this, the thing which we receive here is the value of magnetic field here, which is B, which is equal to mu naught by 2 pi I by r, or we can write it in the form mu naught by 4 pi 2 I by r. This is the same relation which we have derived earlier. So by using the Ampere Circuital Law, we can derive the magnetic field at a distance r from a straight current carrying conductor. Go through the video very carefully. I hope that you have gone through it very properly. If you have some doubt, you can repeat the video again, and still if something is not clear, you can just give me the doubts, post me the doubts so that I can sort it out. Thank you.